Hello everyone, and thanks for tuning in to the final video in the saga of the ant and the goblin. This is going to be an explicit mathematical solution, so you'll need some differential equations, or even if you have some calculus in high school physics, there's a chance you'll be able to follow along and understand the solution. But really it's geared towards master's students at BME in the differential equations course. So let's get started. And I've just left this here. You can pause it and reread the question if you need to refresh, or if you're not familiar with the question. And this is more or less an abstract expressionist portrait of the man who loves this problem more than anyone, but won't explain it to his students. So you can just enjoy that. I think this is a really great portrait. Maybe you weren't expecting to get any artwork in this video since it's a math video, but I thought that would be a nice surprise. So on to the question. And here I've given a more stripped down representation. I just have the ant as a dot with velocity VA going to the left. That's the ant's running speed, which is of course constant. The goblin is still going to the right with velocity VG, and L naught is the initial length of the rubber band. Also, I have y positive going to the right. This just makes more sense. It's a little bit more logical. And above the photo, I have, not above the photo, above the diagram, I have some guys who are cheering the ant on. Alright, that's a license-free photo. They're saying things like, if you make it to the end, you could read that really great book. Or keep going, you're going to love this book. It's a 5-star book. And on the left there, that's just a little bit of product placement. My friend wrote this book. I enjoyed it. It's $10 on Kindle, so give that a gander if you've got some time. And that'll be the last of the product placement, don't worry. So, the problem, we need to write an equation of motion for this ant and solve it. It's plain and simple. And the equation of motion, it's really just like kind of a velocity equation. So, y prime represents the in this equation written here, it represents the ant's velocity with respect to the wall. So all that is the the velocity of the ant, which is going to be going to the left, plus the velocity of the rubber band beneath the ant's feet, which I've written VR band here. It's not V Goblin. Really, the only time it would be V Goblin is at time 0 when it starts and the ant's all the way on the right end of the rubber band, because as this ant is moving towards the wall, the rubber band beneath its feet is slowing down essentially, with respect to the ant. You could imagine it when it's halfway, okay, then it would only be going, or the rubber band would only be going to the right at a velocity of half the goblin speed, because it's on a rubber band. So let's have a look at this. V ant is very easy to put. That's just a constant, right? I think we chose 10 centimeters per second. But the rubber band velocity is changing, so we have to come up with something a little more clever for that. And to do that, you're going to need y of t. This is very simple. We haven't solved for this yet, so we don't know what y of t is. That's okay. We will solve for it. So that represents the ant position, right? At any time, y will just equal where the ant is, how far it is from that left endpoint. And you also need the rope length, or rubber band length in this case, which is the initial length of the rope plus Vg times t. That's just, a velocity times a time will give you a length or a distance. You could imagine after 1 second, the rope length would increase to, I think, 110 centimeters, because the goblin's going at 100 centimeters per second, and the initial length was 10. So from here, you come up with this term. So the ant's position divided by the rope length times the goblin velocity. Let's see why this makes sense for the rubber band speed. I'll pick one situation where, so this would be when time is 0, okay, The ant is on the very right end of the rubber band. So y of 0, his initial position is L0, right? Or L0 over L0 plus, the t term goes to 0, so there's nothing else in that denominator times Vg. This makes sense because at time 0, the velocity of the rubber band where the ant is will just be the velocity of the goblin. So that makes sense. I'll do one other example. Imagine there is a situation where the length of the rope, okay, was, let's just say it was 1,000, or maybe let's go with 10,000. This isn't a real point, but it's just hypothetical, okay? And the position of the ant was only 5,000 centimeters from the wall. If you multiply this times Vg, you'll see the velocity of the rubber band is only half of what it is at the very right endpoint. It's 5,000 over 10,000 is just 1/2. So this will be our rubber band velocity. And just to clarify, that's the rubber band velocity where the ant is. That's where it counts, okay? So now if we substitute that in, we get y for the equation of motion, y prime is VA plus VG times y over L0 plus VGT. And from here, I think this is the hardest part, finding the equation of motion. It certainly was for me. But now it's just a first order differential equation, and it looks kind of nasty in that form, but if you subtract it over, and it's a little bit hard to see, but this is a really nice kind of equation to solve because you can use the integrating factor method. Also called the multiplication trick by some people. So essentially you can come up with kind of a magic factor, multiply it through the equation, and then it becomes very easy to solve because this isn't a separable equation. But there are plenty of YouTube videos out there on the integrating factor method, but let's go through with it. And also, if you're good at that method, you could probably stop watching the video now and just go solve this equation and see if you match my solution at the end. So this is the integrating factor, right? E raised to all that stuff, and all that stuff is just the coefficient of y in this equation, okay? Vg over L0 plus Vgt. And for my integrating factor, we get this here. When you evaluate that, just to be clear, this is a little mistake. This Vg here is not inside the natural log. It's outside of it, so it'll cancel with that Vg. And you get 1 over L0 plus Vgt. And of course we multiply the integrating factor through, and we get this. Then you integrate it. The one on the left looks awful, but really it's just it's kind of like reverse product rule, and it's sort of trivial after you solve a few of these problems. The integral on the right, that's just going to be a natural log, and you end up with this after integrating. So from there, you just solve for c, okay? Get this one. So I'm kind of leaving out the algebra, but I think most of you who are at this level can do that on your own. And we get kind of a long and ugly final position function here. So fortunately, we can simplify this significantly because well, for this question, we want to know how much time it takes to get to point 0. Okay, so when y equals 0, that left end point. So what we're going to do is say that this, we're going to say this equals 0, and because y of t equals 0 at the end point, and then you just solve for t. Okay, so this term will divide out, that goes away, and you're left with this down here. Then after rearranging a little bit, you can combine those natural logs to get this next term. equals -1. And if any of these steps are really unclear to you, you're welcome to post in the comments and I'll add a clarification. So from there, just a little more algebra, rearranging, and you get the final solution for t. That's L0 over Vg times e to the negative Vg over Va minus 1. So that's all. If you have this is kind of like your key to the question. You can solve for any initial length, any initial Goblin velocity, and any initial ant velocity. And this leads us to the question, how much time does it take, and what are the units for time? The velocity we used was centimeters per second, so time will be in seconds. And how much time does it take? It takes a pretty long time. If you substitute all the values in, which I encourage you to do, you end up with this. And for the 10 centimeter per second case, 8.52 times 10 to the 34 years, which is really hard to even imagine. I don't think anyone even thinks the universe is that old. I think this is much older than the universe. So it takes the ant a long time, which is part of the reason why I gave him some cheerleaders. So with that, this will also solve for the case where the goblin goes at 1 kilometer per hour and the ant goes to the left at something really slow, 1 centimeter per second, for example, or 1 millimeter per second. Alright, it's just going to take a lot longer. And I think a while ago when I solved this, I'm pretty sure I changed it because it was overflowing my TI 83 Plus calculator. So I made the numbers a little bit smaller so it could actually handle the computation. This question is important. What if the goblin is friendly? This question was on the first exam in spring 2017 at BME. So instead of the goblin pulling away and making the ant take a really long time, he goes towards the wall. Okay, so he helps the ant out. It's going to speed up this process. Well, what if he's friendly? Will this still work? Well, let's just look at the signs here. If he's friendly, you have, this is the same function. You would get a negative value for Vg now, and a negative value for Va. Okay, so you get e raised to some negative power. This is good. It'll be, since the goblin speed is bigger than the ant speed, yeah, you're going to have 1 over e raised to some positive power. So that should be a pretty small number. Then subtract that by 1. That's going to be less than 1, so it'll be negative. Fortunately, the Vg is also negative out here, this one. Okay, so you end up with a positive term for time. And you can use this same equation to solve the problem. The other one, what if the ant starts at the left endpoint and goes to the right? You'd still solve the same equation of motion, I believe. Yeah. And what you would get is really just a sign change. The time it would take would still be this L0 over Vg times e to the goblin velocity over the ant velocity minus 1. So the sign of that exponent changes. And this kind of makes sense because they'd both be going in the same direction, Vg and Va. So they'd both be positive. If the goblin's going away from the ant, all right, and it's way faster than the ant, you get Vg over Va. Yeah, you get a really big number for that e term. And so this would work for that situation. This is a solution that's, I saw it on a Wikipedia page, but you can also check the Wikipedia page for ant on a rubber rope. It doesn't really go through a very detailed solution, but this is the final answer that they get. They do the case where the ant starts at the wall and runs out to the right end of the rope. So with that, you're welcome to post any questions in the comments. Yeah, I hope you enjoyed the video. I hope this helps. I know the professor doesn't teach us one in class, but fortunately, once you have the equation of motion, it's really a pretty simple differential equation to solve. So if you like the video, go ahead and click the like button. Also, please subscribe. This video took a while to make. And until next time, reckon smoothly.